I love going to Harvey Mudd's graduation ceremony. Just watching all those smiling, proud parents and grandparents as they see the result of all their encouragement, their support, their nagging. It pays off. Here their kids are about to cross over into the real world, into official adulthood. They're about to become one of us, where things aren't always as simple as going to classes or studying for exams. But in that moment, there's just an excitement about the possibility of what's to come, even if it might be filled with uncertainty, even if they don't have a job offer yet or they don't know where they're going to grad school. They're excited because they've graduated and they're moving on. Well, you, my friends, have graduated today. We are leaving behind descriptive techniques and we are stepping out into the world of statistical inference. Now, remember, when we were doing descriptive techniques, that tend to focus on summarizing characteristics about your data, like calculating the mean or plotting the histogram. And it helped us to describe the data set that we were analyzing. But what we weren't able to do with descriptive statistics is to really draw information out of that data set, right? We couldn't make any conclusions. We couldn't do any inferences. Now, we're not going to stop doing that. In fact, we're going to go even deeper. What statistical inference is, on the other hand, is a way that we're going to use our data set to extract information about our populations. And it's going to give us the opportunity to answer real-world questions with near certainty. Now, inference builds on the methods of descriptive statistics, but we can draw conclusions about the population based on data from the sample. Let's do an example in R. Now, anytime we have a random sample, which we could calculate the sample mean from, or the sample variance, or even the standard deviation, what we call those are point estimates. Here, let's load the library data sets. And inside of that library is the data set orange. Now, the data orange has 35 rows, and it has 3 columns. And what this is going to record is the growth of orange trees. Here's a summary statistic. Now, orange has 2 variables. First is age and circumference. You'll see that age ranges from a minimum of 118 months to a maximum of around over 1,500. And the circumference of the tree, as measured in millimeters, ranges from a minimum of 30 to a maximum of around 214. So we can see the means from our summary data, but we can pull them all out directly in the mean function. Here we take the mean of oranges where age is, and notice that the average age of the orange tree is 922 days approximately. Same for the circumference. What's the mean of the circumference orange trees? About 115, slightly over that amount. So a point estimate for the average orange tree age might be 922.14 days. And for the circumference, we could use that 115.85 millimeters. Okay, but wait. Why wouldn't we use the median? In fact, there's really not a reason. The median's a perfectly valid point estimate. Let's check it out for this data set. Here, the median age of the orange tree is 1,004, and you see the median circumference of the orange tree is 115. So another point estimate for the average orange tree age could be 1,004, and for the orange tree circumference could be 115. Now, wait a second. Did you just catch how close the sample mean circumference is to the sample median circumference? It's 115.85 compared to 115. And not only that, look at how far off the tree age estimates are, 922.1 to 1,004. So which estimate is better? And how are we going to decide between the two? Well, I'm excited because that's exactly what we're talking about today. Statistical inference is the process of making an estimate, a prediction, or even a decision about your population based on your sample data. So what can we infer about a population's parameters based on the sample statistics? In other words, what are we going to gain when we sample and we draw this inference? Well, here's the rationale for that. Large populations make investigating every single person in the population impractical, and it's expensive, right? So if we had a population and we wanted to know some characteristic about it, we're likely not going to be able to sample every single person, right, to get their measurement or get their opinion or collect their data. So what's easier and oftentimes cheaper to do is to take a sample. And from this sample, we want to make estimates about the population. But those estimates aren't always going to be correct, right? We have to build into the statistical inference measures of reliability, namely a confidence level, which we're going to talk about in this lecture, and a significance level, which will be in the very next lecture. And so statistical inference helps us do those two things: draw conclusions about a population or a process from sample data. It's also going to give us the ability to provide a statement of how much confidence we can place in those conclusions that we draw. Now, the objective of estimation is to approximate a value of our population parameter, right? So we got our data, we want to collect a sample statistic, and then we want to estimate that and see how close it really is to our population that we're interested in. Now, we can estimate with both points, a point estimator, or interval estimators. The most common point estimate is the sample mean, and we use that to estimate the population mean, mu. Now, the reason it's pretty common is because it's the best. We'll see in a second. It's unbiased, it has minimum variance, and so the mean is used commonly, not just because it's easy to calculate from our data, but because it's actually the most efficient estimator. Now, a point estimator gives us a particular value to estimate our parameter with, whereas a confidence interval, well, that gives us a range of possible estimator values. Now, for this lecture, we'll focus on point estimates, but next time we'll talk about confidence intervals. Let's define that. A point estimate of a parameter, say theta, is a single number that can be regarded as a sensible value for theta. And here we're using theta generally. Theta could represent the mean or the variance or the proportion. Now, we find a point estimate by selecting some suitable statistic and computing its value from the given data. Now, what we call that statistic is the point estimator. The point estimate is the actual value, right? Once we collect the data, we get a value. The point estimator is the statistic. And so we usually use theta hat to denote the point estimator of a parameter theta. Now, in inferential statistics, you'll often see Greek letters used for populations. And for this sample, what we do instead is the Greek letter with a hat on top. So if you see a theta hat or mu hat, that's going to tell us that our point estimate is for the sample. Now, different statistics can be used to estimate the same parameter. Maybe a parameter can actually have multiple point estimators. Let's look at another example. The woman data set in R has the average heights and weights for American women ages 30 to 39. So this is a sample of 15 women with those two variables, height in inches and weight in pounds. Here's how we'd load that data into R. So data of women, and then attach it because we want to call some of those variables. And let's look at the summary statistics for that data set. Here you see the height and the weight of the first 6 points. Height starts at 58, 59, and it's increasing. And a weight, 115. I don't know what woman in America they got for that, but it definitely wasn't me. Let's look at a scatter plot of that data. It almost looks too good to be true. But here's the plot of height and weight, and we clearly see a relationship. As height increases, weight increases, and vice versa. Now, we can generate point estimates for the population parameters based on our sample statistics. In this case, let's think of 3 sample statistics that we can take from that data. The first might be the median. So the median value for height is 65 inches, and the median weight was 135. Likewise, we could estimate the mean with a 65-inch height for the mean and a 136.73 weight for the mean estimate. And we could even do estimation on the standard deviation. In this case, the standard deviation for height is 4.47 inches, and for weight is 15.5 pounds. But you might ask yourself, okay, we've already learned about mean and median and standard deviation. Are there any other estimators we could use to actually estimate our population mean parameter? Well, I'm glad you asked. A couple might be this one, the average of the extremes. So maybe our mu hat could be equal to the minimum value in our data set plus the maximum value divided by 2. In effect, we're sort of taking the range and halving it. And so it's giving us a measure of the center of the data set. Another point estimate that we use in statistics is called the trimmed mean. So mu hat equal to x bar, but it's trimmed. In this example, a 10% trim mean means that we're going to discard the smallest and the largest 10% of our sample, and then we take the average. All right, check out this graphic. Here we have a plot of the population distribution with an unknown parameter of interest. In this case, let's just say it's the mean, mu. Now, we collect a random sample from our population in an attempt to get a good estimate of mu. We're going to call that mu hat. Now, since we don't know how close we are to the true population parameter, we have to be strategic in selecting our point estimator. In other words, we want our point estimate to follow certain rules so that we know our sample estimate is going to be close to the population estimate. Now, the million-dollar question is this: how do we choose an optimal estimator? Right? Now, get this, a point estimator is a random variable, and its value is going to vary from sample to sample. Right? If you take a sample and I take a sample and we both calculate the sample mean, they're going to be slightly different. And so we actually have a name for that variability. We call it the error of estimation. The error of estimation is equal to the difference between theta hat, so our sample statistic, minus theta, our population parameter. So if we solve for theta hat, we see that theta hat is equal to theta plus the error of estimation. What this says is that we want our optimal estimator to be really close to theta, but plus maybe a little bit of noise, a little bit of error, because we're probably going to be off a bit. So which is the best one? Well, here's how we're going to pick. We want to choose an estimator that is unbiased. So this is the one that's closest to the true value of the parameter theta on average. We also want to choose an estimator that has minimum variance. That just means it's the one with the smallest estimation of error, the smallest variability, the least spread. That's the estimator we want. All right, look at this graph. Now, ideally, an estimator should have low variability. So we want it to be precise, but we also want it to have low bias. We want it to be accurate. And so we're looking for an estimator that has both low bias and low variability. That's going to be the best estimator for us. We talked about bias, but you may not know what that is yet, so let's define it. An estimator is unbiased if, when I take the expected value of it, it gets me back to my population parameter. So the expected value of theta hat is equal to theta. Now, if theta isn't unbiased, we call that difference, the difference between the expected value of theta hat and theta, the bias. Now, it's important to realize that other estimates exist, like the range or the average of the largest and smallest values. But these estimates are not unbiased, and they shouldn't be used to estimate the mean. Here are some unbiased estimators. So our sample mean, x bar, is an unbiased estimator of the population mean. Also, for continuous symmetric distributions, the sample median and the trim mean are also unbiased estimators of the parameter. The sample variance, S squared, is an unbiased estimator of the population variance. Let's put that into practice. Suppose we have a binomial distribution. So X is binomial with parameters N and P, where we don't know what P is. We can show that our estimator, P hat, which is x over n, is unbiased. So we do that by taking the expected value and showing that it gets back to the original population parameter. Notice here, when we take the expected value of p hat, we can plug that in. That's the expected value of x over n. Now, 1 over n is a constant, right? So an expected value, we can pull that outside. So pull out 1 over n, and you're just left with the expected value of x. Now recall, from a binomial distribution, our expected value of x is n times p. And so we plug that in. Notice that those n's cancel out, and that gets us back to our population parameter, p. We can also show for a normal distribution that the sample mean is an unbiased estimator of mu. Let's do that together. If we take the expected value of x bar, we can plug in x bar, which is just the sum of xi over n. There's that 1 over n again. We're going to pull it outside of the expected value, so we have the expected value of the sum of xi. Well, this is just the sum of the expected values of each of those, times 1 over n. Now, our random variable x has mean mu, so that's the sum of n of those mu's. Notice that 1 over n times n mu is going to cancel out to get us back to our population parameter, mu. Now, an unbiased estimator is going to be consistent if the variance of that estimator approaches 0 as our sample size goes to infinity. In other words, the difference between an estimator and the population parameter becomes smaller and smaller as my sample size increases. Here's an example. The sample mean has a variance of s squared over n. Now this variance goes to 0 as the sample size increases, right? Because my n goes to infinity and that variance term gets smaller and smaller. Here's another example. Suppose instead we were looking at the mean by averaging the first and the last values. Okay? We showed that this estimator might be unbiased because look, the expected value of x1 plus xn over 2, we can split that up. The expected value of x1 over 2 plus the expected value of xn over 2, which is mu over 2 plus mu over 2. Great, gets us back to the population parameter. But what about when we take the variance of that estimator? It doesn't go to 0 as n increases. In fact, it stays fixed. Look at this, the variance of x1 plus xn over 2. When you split that up, you're still left with s squared over 2, no matter what your x1 and your x2 are. The second quality we want in an estimator is efficiency. Efficiency, we have the option of choosing between two unbiased estimators. Which one are we going to pick? Well, I would say let's choose the one that's more efficient. All right, what do we mean by that? Let's say we've got a normal population. We've got both the sample mean and the median are both unbiased, but the sample median actually has more variability than the sample mean for a fixed sample size. We could simulate this in R, and I want to show it to you now. Right. Here we've done set.seed. So what set.seed does is fix the random generator that R uses when it simulates data. We're going to create our data matrix X. And cbind means I'm going to bind these variables by column. So column bind. And here's what we're doing. We're simulating 100 random, normal, 0 mean, standard deviation of 1 random variables. Right? So we simulate 100 of them and then put them in rows. In fact, we put them in the columns of X. And now I want to take the mean of those 10 samples and the median of those 10 samples. So apply X, mean, and 2 is telling R that, hey, I want to look at each of the columns and I want to take the mean of the columns. And then apply X to median says, look at the columns again and take the median of those columns. Here's what we get when we do that. First row has the mean values for all of my simulations, and the second row shows all the median values for those simulations. Now, what I really want to do is then take the average of all of those means, right? I want to see how does my mean perform in that entire data set. Notice here, the average of my means is negative 0.027. Whereas the average of my medians is negative 0.04. Okay, if you're lost right now, let me clear this up, because here's what I want you to get. We simulated data with a mean of 0 and a standard deviation of 1. So we know that the true underlying population is normally distributed and it should be centered at 0. So each of our estimates should be close to 0. But notice that when we use the means as an estimate, we were only off by minus 0.027. Whereas when we use the medians of the estimates, we were off by minus 0.043. This is what we mean by efficiency. The mean as an estimator is more efficient than the median because its variability is smaller. It gets us closer to the estimate. We can also look at the variance of those two estimates, right? So if we take the variance of the mean, it's 0.008. But notice the variance of our median estimators is 0.026. Again, the mean outweighs the median. Now, if we wanted to denote the precision of an estimator, we can use its standard deviation as a measure. But now in inferential statistics, we don't call it that anymore. We've upgraded. Remember, we've graduated. So it's something slightly different. We call it the standard error of an estimator. So sigma theta hat is the square root of the variance of theta hat, which we now call the standard error. Now, the estimated standard error, it can be denoted by either sigma theta hat or S theta hat. You may also come across SEE, which stands for standard error of the estimate. Now, our point estimates are going to satisfy some really neat properties, and they're fundamental to drawing inference out of our sample. The point estimates from a sample can be used to estimate our population parameters. But there's variability in the point estimates. They can change slightly with each sample that we take. And so we're going to quantify that uncertainty by looking at its standard error. Now, we come across a few pitfalls when we're working with population parameters and our estimates. And here are a couple of them. Remember, our point estimate is only going to be a single number for our population parameter. It's a good number, but it's just 1 point. And there are lots of different types of point estimates that we could use on the same data set. So you could generate several point estimates, and I could generate several of them. It's really too many to logically choose from. And for each estimate that we generate, it has its own standard error associated with it. So the problem becomes then, how are we going to pick the best estimator? Well, we've shown that if our estimate is unbiased, and if it's efficient, and if it has precision, that makes a really great point estimate. But is there a better solution? Perhaps we could give a range around our estimate. Maybe take our estimated value and go a little bit above it and a little bit below it. And that might give us a better idea into what real values our parameter can take on. This we call the confidence interval, and we'll talk about it next time.